Hi there, this is the video for Vectors 1, which is the kind of GCSE recap and an overview of the key vector properties. This unit actually, although it's being taught in Applied, is actually a pure unit. It's chapter 11 in the pure kind of year 12 work. We are teaching it as part of Applied because you will need it for Applied as we go through the course. What that means is we'll start by looking at vectors in abstract really, and then towards the end we'll start looking at them in an applied mathematical context. So at the moment we're just focusing on the kind of pure, how you use vectors in maths, and then we'll start looking at the more applied side towards the end of this unit, toward the end of this chapter. So this is a pure chapter, but we're teaching it in applied because we'll need it sooner. Now the first thing we need to think about is how we can define a vector. Okay. Now what actually a vector is? This is something you should know from GCSE, but vectors describe a displacement in space. Okay. They describe how some displacement, some movement between 2 points has happened. Okay, so from A to B here is a displacement in space, and I have two key properties. Okay, something is displaced with a certain magnitude and a certain direction. Okay, and they're the two defining properties of any vector. A vector has to have a magnitude and a direction. Okay, it has to have a magnitude and a direction. Now that magnitude can be zero. Okay, you can get zero vectors, but both of these things have to be there, magnitude and direction. Now, we can think of magnitude as length. Okay, that's how we represent magnitude in our diagrams of vectors. It's the length of that vector, which is the magnitude. We also need to recall the three key ways in which we note vectors or denote vectors. Now, each of these you've seen before, and we will be introducing a new way in this unit as well, but we're going to just recap the first three before we go on to that. Now, the first one is by defining it by its endpoints. Now, this vector I've got on the screen, A to B, I can write like this. The vector from A to B, this arrow, denotes the direction I'm going from A to B. Okay. If I reverse this vector, I'd then write this the other way around and put B to A. Okay, BA with an arrow on top. So we can define them like this, we can write them like this, and you will see that regularly in textbooks and exam questions. Sometimes the vectors will be defined in and of themselves. Okay, I could define a vector A that could be the vector AB. Okay, it could be this vector A, and on the screen I'll always write them in bold. That's a convention. So on the screen or in textbooks they'll be written in bold. Now in your books you need to make sure you're underlining your vectors to make sure that you can tell the difference between a vector and a scalar. If you don't get into this habit early, it will cause problems for you. Okay, we see this regularly, students who are not used to underlining vectors and then get confused about which, especially when later on we'll start using algebra and vectors, which letters denote a vector and which letters denote a scalar. So get used to underlining anything that is a vector, please. The third way is column vectors, and you saw these at GCSE when you were looking at translations, and also you saw them when you used them as column vectors. Okay, so you should be used to this with the top number denoting any movement in the x direction, so horizontally, and the bottom number denoting any movement in the y direction, so vertically. So this, for instance, would be 4 steps to the right and 2 steps up. Now we'll use all three of those notations. We will, as I say, introduce another one, but that will be in the next video. Before we move on to a couple of examples and kind of GCSE style questions we're going to recap, I like to just look at some key kind of principles of vectors, or key properties. Now the first is how we can define vector equivalence. By that I mean how two vectors can be equal to each other. Now, as we've said, the defining property, the two things that define a vector are its magnitude and its direction. And so for two vectors, for instance A, B and C, D, to be equivalent and equal, if they have the same magnitude and the same direction. If one of those two things are different, they are not equal. So I have these two, A, B and C, D, and these two are equal to each other because they have the same magnitude, represented here by the length, and the same direction. These arrows are pointed in the same direction. Now, as we can see here, these two vectors are equivalent, but they're not in the same place. Okay, vectors are not defined by a specific point in space, like a coordinate is. Okay, so I can have two vectors could not be in the same place. I could draw this vector all the way over here. Okay, I could draw it in Australia, and it would still be the same vector. Okay, it does not matter where I draw it. It is the same vector if the magnitude and the direction are the same. Now, in part because they can be drawn in different places, we can also tell that any equivalent vectors, which are going in the same direction or have the same direction, will also be parallel. Okay, so equivalent vectors will always be parallel, and we'll look at parallel vectors in a second. And a couple of examples or non-examples here of vectors that kind of could be misinterpreted as equivalent. Now these two, they maybe have the same magnitude, okay, but they are going in a different direction. Okay, so these two are not the same vector. These two are going in the same direction and are parallel, which is what we'll look at in a second, but do not have the same magnitude. So here the direction is different, here the magnitude is different. The next key property, or next kind of thing we need to be very aware of, is multiplying a vector by a scalar. Okay, now multiplying a vector by a positive scalar, and we'll talk about negative scalars in a second, but positive scalars changes the magnitude of a vector, but not the direction. This again is something you've seen at GCSE. So for instance, if I'm doing this multiplication, 3 lots of the vector 2, 5, I get 6, 15. And there's no change of direction there. If I drew both of those, I'd have no change in direction. I'd only have a change in magnitude. If the scalar is negative, though, then the vector will change direction. The magnitude may well increase. If I multiplied this by negative 3, I'd still have 6, 15, but I have negative 6, negative 15. That would mean that my direction had flipped as well. So for instance, if this is the vector A, and if I multiply it by the negative scalar, which is negative 1, I get the exact same magnitude vector in the opposite direction. Okay, if this is negative 2, it would be twice as long in the negative direction. Okay, so if scalar is negative, then it will change the direction as well as the magnitude. Okay, but it will just flip the direction. It won't rotate the direction or anything like that. Now, as promised, parallel vectors. Again, you should recall from GCSE that we can define two vectors as parallel if we can write them in this general form. Okay, we're going to kind of formalize this. You might not have done it as formally as this at GCSE, but two vectors A and B are parallel if we can write them in the form A equals lambda B. Okay, this is a Greek letter. It's called lambda. So A equals lambda B, where lambda is a scalar. Okay, as long as lambda is a scalar, then these two will be parallel, and that is in part because if I multiply something by a scalar, it will not change the direction. Okay, it might flip it, but these two are still parallel. Okay, if lambda is a negative number, they're still parallel because it's flipped, but the line hasn't rotated and moved out of parallel. Okay, so this is our definition of two parallel vectors, sorry, and this is how we're going to prove two vectors are parallel. We'll have a look at a question like that in a second, but I've got A equals lambda B is the way I can prove that any two vectors are parallel to each other. Another one, vector addition, probably one of the easier things, and I think something everyone should be comfortable with. But I know that if I have two vectors, A and B, I can add them along the pathway and create a third vector, C. And that will give me a simple expression, A plus B equals C. Okay. Now, I can also apply my usual rules of any kind of equation, and I can, say, subtract A from both sides, and I'd get this expression, B equals C minus A. Okay. Now, I can also show that on my diagram, because here it's C, so I'm going to start from here. I can add the vector C, and then subtract, because I'm going backwards along it, I subtract the vector A, and it clearly gives me the pathway B. Okay. And I can also see this on this side, where I've got negative A plus C, which is the same as C take away A. Okay, so adding vectors is easy to do along a pathway. Okay, I know I can do A plus B is C. I know I can do C minus A minus C will give me A. And so, it will give me negative A because I stopped at the top. Started at the top. And the other important thing is if I add two or more vectors, that is the resultant vector. Okay, we call the sum of two or more vectors the resultant vector. We're going to go through a couple of example questions now. These are kind of high-level GCSE questions, right? They're questions you should be comfortable doing. We'll go through them step by step. The only difference here is I'm not giving you diagrams, but that's nice and easy. So if I have a triangle ABC where the vector AB is A and the vector BC is B. The point D intersects AC in the ratio 2:1. I want to find the vector BD in terms of A and B. Now that's loads of information and it's difficult to digest right now, so the first thing I'm going to do, I know it's a triangle, so I'm going to draw a triangle. Doesn't matter what that triangle looks like. I'm going to label the sides A, B and C. Okay, and I'm going to start labeling any information I'm given in the question. I'm told the vector AB is A, so I'm going to label that. I'm told the vector BC is B, I'm going to label that. I'm told that the point D intersects AC in the ratio 2:1. I'm going to use that information in a second. Okay. And I know I need to find the vector BD in terms of A and B. Okay. Now this diagram is now much more useful for me. I've synthesized all the information and straight away it's going to help me. Because I want to find the vector BD, I want to think about what pathway I will take to find the vector BD. And I'm going to do BD is equal to BA plus AD. Okay, you could go the other way, but this is the way I've chosen. Okay, you'll get the same answer. It doesn't matter, but this is the way I've chosen. B to A to D. Now straight away I can tell what BA is. Okay, I should know that this will just be negative A, and that's useful for me. But I don't yet know what AD is. I've not got any information about that yet. So I need to think about how I can find AD. And I've been given this ratio, so I first need to find what AC is. Okay, so just to one side, the way I'm going to work it, AC is equal to AB plus BC. AC is AB BC, so that is A plus B. Okay, and then I've got this ratio to work with, that A to D and D to C is 2:1. Okay, now that means that 2/3 of AC to 1/3 of AC. This is the same thing. This is just in fractional form, okay? And I can put that on my diagram straight away if that's useful. Okay, if you can see 2/3 to 1/3, if that's useful for you. But that means that AD is 2/3 of AC and DC is 1/3 of AC. Now I've got all the information I need to plug into this expression. BD equals BA plus AD. So BA plus AD. BA is negative A, as we discussed, and AD is 2/3 A plus B, as we found here. Okay. Now all I need to do is just simplify it. It's a bit of a mess, so I want to expand and simplify. Okay. So negative A plus 2/3 A minus 2/3 B, and we should be comfortable now. That's 2/3 B minus 1/3 A, and that's my answer. Okay, simple as that. One more example. OAB is a triangle where OA equals A and OB is half B. The points M and N are midpoints of OA and OB respectively. Show that MN is parallel to AB. Now again, too much information, I need a diagram, so I've got a triangle again, and it's OAB. Okay. Now, I'm told that OA is A, I'm told that OB is half B, and I'm told that M and N are midpoints of OA and OB respectively. So I want to show that MN is parallel to AB. Now this is the key word here. MN is parallel to AB. So straight away, I know that if it's parallel, AB equals lambda lots of MN, where lambda is some scalar factor. Okay, I know that AB equals lambda lots of MN. Now, if that's true, I want to test that that's true. So I want to find, and the way I can test that that's true is if I've independently find an expression for AB and an expression for MN. So that's always going to be my process when I'm looking to prove that two things are parallel. I'm going to look for AB. Now AB, I've jumped a step here, but you should be able to see quite easily. A to B is negative A plus half B. And it can be easy just to trace that. Okay. And if it helps you, please do write out A to O, O to B. Okay, absolutely happy for that. But negative A plus half B. MN, which is slightly more difficult, is M to O, O to N. Now I'm told they're midpoints, okay? So M to O is going to be negative a half A, okay? Because it's halfway between A and O, and that's negative A. So M to O is negative a half A. Now O to N is halfway along this, so halfway along half times B, along the vector half B. So it's a quarter B. Okay. Now these can be substituted into my expression. Negative a half A plus a quarter B. Okay. And here is the part where I need to compare them. Go back one step. Mn is negative half a plus a quarter b, and ab is negative a plus a half b. What I need to look for, what's this factor? Can I show that if I multiply this expression by some scalar, I get this expression? And as I showed you a second ago, my factor here is 2. Some of them are easy to see, some of them are harder to see. Right? You'll get better as you do them, it can be practice, but try some numbers if that's easiest. Okay, like half to get to 1 is obviously 2, check the other coefficient and it works. Okay, once I've shown this, that means AB is 2 lots of Mn, and I can say that therefore AB and Mn are parallel. Okay, that's it. As long as I've proved that this is true, and shown that there is a number for which this holds true, then I can say that they are parallel, and I'm done.